Hi, and welcome back to my Physics Online video lecture series. Today's video, I'm going to be talking about the speed of sound. Now that may seem like a very narrow topic for a video, and it's maybe a little more narrow than some of the others that I have, but there's more to it than just simply talking about how fast does sound travel in air. So I will be mostly talking about how we how we calculate the speed of sound for air and for maybe some other media, and then some other reminders about how speed is related to some of the other parameters of our wave. All right, so that's where we're going in this video today. So this First of all, what is speed of a wave in general? Any wave, be it sound, be it a wave on a string, be it longitudinal waves, electromagnetic waves, transverse waves, longitudinal waves, electromagnetic wave, wave on the ocean, all of those, this relationship holds as true. The speed at which the wave is propagating is equal to the wavelength times the frequency, which in turn is the wavelength divided by the period, which in turn is the angular frequency omega, or omega naught, whichever you tend to use, divided by the wave number. Okay, so as long as you are dealing with a single wave, not a wave pulse, this one right here holds true. Wave pulses are a little more complicated because they involve multiple waves that have multiple different periods, multiple different frequencies. But this right here works for any of the waves that we'd be talking about in an introductory physics course. So that's the first thing. What about speed of sound specifically? So sound waves specifically. Mechanical waves, and sound is a type of mechanical wave, tend to have speeds that are related to typically the square root of some sort of elastic restoring force divided by some sort of inertial term. So mechanical waves in general would have this relationship: V is equal to square root of elastic restoring force divided by inertial terms. And of course, inertial terms generally mean terms related somehow to the mass of whatever medium is carrying the wave. So inertial term for the medium. So that's kind of your basic, this is what your speed will be determined by. So wave on a string, as a reminder, wave on string, what we had was V is equal to square root of the tension force divided by the mass per unit length. So your elastic force is basically the force of tension within the string. This also works for a wire, by the way. A plucked wire, like a lot of guitar strings. You have your steel guitar, it's a steel wire of some sort. So that is your speed of sound, is your transverse wave speed for a one-dimensional wave. Now again, the point here is that we want sound waves, not just any old transverse wave. So sound waves can be one-dimensional. For example, you can have a material that is essentially like a rigid rod like this, and you can have a wave propagating along it, a sound wave. So let's call this a rigid rod. The density of the rod is given by rho. And then the restoring force term, looking at this right here, looking at these units, this is force divided by mass per length. And so dimensional analysis wise, you're looking at force over mass over length, and then you're taking a square root. And so then coming out here, we expect that those units will add up or multiply out to speed, meters per second. So my density has changed from a mass over a length to a mass over a volume. So on the bottom, my density term is now mass per volume. So I need to multiply the bottom by an area term. So now one way of doing that is to have force over area as my numerator term. Okay? And force per unit area, you might think, oh, that's the pressure. It's not really, though. Remember that force per unit area, yes, pressure is a force per unit area, but we also have moduli of elasticity. So we're expecting this to basically be a modulus of elasticity divided by a density. Okay? And for a rigid rod, the relevant modulus of elasticity is Young's modulus. So for the rigid rod, this comes out to V is equal to square root of Young's modulus for elasticity divided by the density of the material. Okay? Now, rigid rod is kind of a special case. Most of our interactions with sound waves, most of them, are stuff like I'm talking into my microphone, into my computer, and you're hearing it. Perhaps you're hearing it through your headphones. Perhaps you don't have headphones, you've got speakers, and the wave is propagating to you from those speakers. In other words, it's coming through open air at you. And that propagation is not a one-dimensional wave. Not really, anyway. It's more like a three-dimensional wave. So in a three-dimensional wave, we replace the Young's modulus with the bulk modulus of elasticity. So V is equal to square root of the bulk modulus divided by the density. And this is in 3 dimensions. If you want that in a fluid, then this happens to be equal to some calibration speed times the square root of the temperature divided by the calibration temperature. So this is 3D in fluid. So gases, liquids, that kind of thing. All right. And for depending on the fluid, you basically go look up the calibration temperature. So T naught represents calibration temperature. Usually it's 0 degrees C, or room temperature 20 degrees C. But it could be any temperature. So this is calibration temperature, and then V naught is known speed at T naught, that temperature. And T represents actual temperature. So that's what those terms all represent. Okay. For air, sound in air, V naught is approximately given as 331.4 meters per second at T is equal, or at the T naught is equal to 273.15 Kelvin. That's the important thing about this equation. These temperatures are in Kelvin. So in Kelvin, so what is 273.15 Kelvin? This is the same temperature as 0 degrees C. But you want the temperatures to be in Kelvin. Okay? Quick example, and this is a good one. What's the speed of sound in air at room temperature? So, room temperature, T equals 20 degrees C is 293.15 Kelvin. So V would therefore be 331.4 meters per second times the square root of 293.15 Kelvin divided by 273.15 Kelvin. Alright, so you'd want to enter that into your calculator, and what you would get is approximately 343.318, so let's call this 343.3 meters per second. So usually what we end up doing is we say speed of sound in air at room temperature, by the way, 1 atmosphere of pressure, that's also important. Speed of sound, V, is about 343 in air at room temperature. What happens if you choose a different medium? Well, then the speed of sound will tend to be different. For example, we could look up for some other medium, let's say at 0 degrees C. And what I have here is a little table of values that I pulled from the OpenStax College Physics book, the open resource book. So this is speed in various gases at 0 degrees C. Notice that this is retaining only to the nearest whole number, so 331, it's rounded down from 331.4 meters per second. And then also some liquids, and notice that in general the speed of sound is faster in liquid than in air or any other gas. Hydrogen being maybe the one exception, and really just compared to some liquids. Okay. Here's a fun one. If I create a sound wave with a given frequency, be it in air, be it underwater, whatever, and I measure the transmitted sound wave. So maybe I have something in air and there's a transmitted sound wave under the water surface. Not very much of it gets transmitted. That's for a different lecture maybe. What stays the same and what changes? Well, obviously the amount of energy changes at the interface. Most of the wave gets reflected. But the frequency that it's generated at fundamentally remains constant across the two media, and so because the speed changes, the wavelength must also change. And so very fast frequency means much longer wavelength. Fast speed, long wavelength.